I'm excited to now present the PI of this amazing project. So take it away, Taryn.
Thank you, and thank you really for this opportunity to share this work. We spent a lot of time and effort on this project, and we're hoping that people will build on it. So thank you for the opportunity, Madison. Thanks to Ronnie for the introduction to this project. So as Ronnie mentioned, the first half of the project was all discipline specific, and the second project was trying to put all the pieces together. And so that's what I'm going to talk about today. Okay, so some of our goals were, as Ronnie mentioned, reanalyzing and synthesizing existing multidisciplinary data from different Alaska volcanoes and different eruptions from the same volcanoes. Our goal was to identify patterns prior to, during, and following unrest or eruption, and then to use these to develop models, as Ronnie mentioned, ultimately integrate these into volcano-specific eruption forecasts. How did we do this? We thought it might be helpful to just go through like actually how we did this, because it was a little bit iterative. We learned along the way. But basically what we did is each student was assigned 2 volcanoes that they were going to lead. We had a template slide deck that we prepared. Each lead student was in charge of providing an overview of the eruption chronology based on AVO annual summaries or the website. And then each discipline group was responsible for reviewing all the existing data and literature under their discipline and adding the highlights to the slide deck. We then went through internally and had a presentation where we presented, each of the different components we added. We discussed possible interpretations, and then the lead student was in charge of, using those to make further interpretations and come up with a conceptual model. We then had a second meeting where we invited all PREEVENTS collaborators and all AVO people to join as a quality check. This is what we're thinking. Is there something we're missing? Is there something we've overlooked? And then we went into kind of drafting an outline of a paper to move forward. So that's kind of the overview of that. And another thing that was really helpful for this multidisciplinary data synthesis was developing the database and also this multi-plot tool where the data could be viewed. The database part got started a little later than desired, but the goal was that all these new products we were developing, they're not data, they're data products, and they didn't have a home like Iris. So where are we going to put these data? So we contracted with the research computing part of our institute. So they helped us to develop this database with the idea that we'd include all the PREEVENTS products, but also all the other data that AVO was already using. So they could all be pushed to this one data viewer. We call that data viewer the multi-plot tool. I'm showing an example here. This is from Shashalden. This is showing 10 years of data. And it's basically like a big drop-down menu where you can pick which discipline, which data set you want to look at, and which time series you want to look at. So this is just some of the examples in the data in the multi-plot and the database. And you can see, variations in these different parameters as volcanic activity changes. The multi-plot tool is currently available for AVO internal use, and I would say some of us use it quite regularly. It's pretty helpful. The database is still in progress. We have the remote sensing data and most of the seismoacoustic data in there, and I think we're still working on deformation. Okay, so now I'm going to switch and go into the volcano-specific synthesis that the students led. So this is Darren's work on Pavlov, and I think Darren has a lightning talk on this later, so you'll hear more about it. But basically the goal was to integrate, whatever data, multidisciplinary data were available. And in this review, Darren found out that there seemed to be a difference in eruption style, specifically explosivity and eruption duration, as a function of vent location. So sometimes Pavlov erupts from a southeast vent, and sometimes it erupts from the summit. So Darren came up by combining the multidisciplinary data. He came up with a conceptual model where he has this T-junction and probably parameters such as magma ascent rate and possibly vent sealing and other parameters might influence which is the dominant pathway. And that could control the differences we see. If you're not familiar with Pavlov, the 2016 eruption was extremely explosive, and everyone was like, "What happened there?" So this is one of the ideas that came out of it. Lessons learned from this synthesis: machine learning methods are really useful for processing decades of data. Also, importantly, seismoacoustics is very helpful for interpreting the shallow system. But if you want to link that with deeper systems, it's helpful to use the complementary data sets. Okay, moving on to Mario's work on Shashalden. So again, integrating multidisciplinary data, geodesy, seismology, gas, and petrology. He was working to develop an updated conceptual model. There was a nice conceptual model from Rasmussen et al. Showing basically a vertical conduit with no obvious storage region beyond within the conduit itself. But what Mari was able to do is actually identify deformation. So he identified a pressurized source at about 2 to 4 kilometers depth, which is a similar depth to what Dan found for magma stalling. But this was a pressurized spherical source, so the interpretation is this might be a small magma reservoir. So lessons learned, Shishaldin deforms. This was really exciting for us. When we wrote this proposal, we called Shishaldin an open system volcano. Part of that definition included that it didn't really have any obvious deformation. So a key lesson, I think, for a lot of us is that some of these volcanoes that might not have obvious deformation, it might be just inherent to our detection limit. And in this case, using the really long time series of GNSS data enabled them to pull out the signal. Okay, let's see, moving into readout synthesis. This was led by Jamshed. And so what he did is what they did was combine the petrologic information with the other multidisciplinary data available. Readout is a little bit unusual in that there was a lot of multidisciplinary data available, which is great. So their interpretations of this eruption is that there was probably a long period of magma injection underneath readout between the last eruption in 1989 and then 2009. And then the 3 months prior to the eruption, there was probably a substantial increase in magma intrusion. And this figure from their paper shows a bunch of different monitoring metrics. And what you can see is that really in those 3 months before the eruption, there was a big increase in those parameters. So linking the diffusion chronometry with these other data sets really helps pull out some of the different signals and can really complement the real-time monitoring data. And it was particularly useful here because there were so many monitoring data available. And then they note it's very important to collaborate with disciplinary experts, which I think is an overall lesson we all learned through this project. Jamshed also led the Boguslav synthesis. And I think, they presented on this earlier. So you might have got a little precursor to this. But again, using diffusion chronometry, looking at both samples after the eruption already happened and interpreting that to reflect decompression magma ascent, and then looking at diffusion chronometry on crystals prior to the eruption, interpreting that as magma recharge. And I think I already mentioned those lessons learned. Okay, then moving on to the physical modeling. This was led by Tara Shreve. What she was aiming to do was use a 2D finite element model, COMSOL, to estimate surface temperature and subsurface pressure, simulating hot steam passing through a stalled lava dome. The idea or the ultimate motivation was really how do we interpret these thermal anomalies we see at volcanoes, and can we say something about the subsurface from these thermal anomalies? So using this model, she was able to identify a linear relationship between changes in the surface radiative flux, so the heat emissions, and then the pressure underneath the lava dome. And it seems like this is related to the steam pathways, and particular the fracture network, and if those fractures are sealed or not. So she has a paper that is currently within co-author review and hopes to get that published soon. The next part of her work would be then to apply it to a volcano. So she has done some preliminary analysis on Cleveland, which is a great target. It has a long-lived dome, often has thermal anomalies, and what you'll hear in the next talk, maybe as part of the AVO AVERT project, this is the only volcano that has real-time gas data. This is from 2 scanning DOAS networks. So she will be able to use the continuous SO2 time series since 2002 and the satellite radiative power estimates to test her model. One of the key lessons learned for her project was really to think about the availability of data to test your model before you get too far into your project. It's really nice to have data to validate your model, and we don't have it at many of our volcanoes. And then moving on to Vanessa. Vanessa led the statistical modeling portion of the project. Her first project was really to distinguish between background and unrest. Maybe this is obvious to everyone, but it was surprising to me how difficult it is to differentiate between background and rest until I worked at Volcano Observatory. So what Vanessa aimed to do was really use statistical tools to try to tease out these different parameters. So she combined 4 anomaly detection methods, 2 statistical and 2 machine learning, and then she used bootstrapping to combine them all to come up with an overall recommendation of the anomaly. She applied this to about 12 different monitoring metrics and that I have listed on the next slide. And there's a figure here, an example from Augustine volcano. So she manually went in and identified the periods, defined them as unrest, quiescence, eruption, and then post-eruption. And then her technique identified, sorry, you can't read it very well, but basically this is the lower threshold of anomaly and this is the upper threshold. So somewhere between those values is probably identifying volcanic unrest. So the data she was looking at mostly at thermal parameters, gas parameters, and seismicity. Those are the 12 metrics I mentioned. To do her manual classification or her labeling first, she went through the AVO logs and the AVO annual summaries to come up with a historical chronology for all the observations, and then she used the time series data. The lessons learned are that the data variability is hugely variable across disciplines, time, and volcanoes. So it's really hard sometimes to pull all these pieces together to make these quantitative thresholds. It only works if you have enough data to do it. And then the second thing that was really important is that characterizing these episodes really depends on the reports available, and these are often non-standardized. They may be biased, they're often incomplete or absent. So for example, steaming was a parameter that was identified as important for readout, but an AVO's daily remote sensing checks, it's only required to report steaming in webcams if the volcano is at color code. So this is just one example of the biases of how our operations may lead to biases in interpreting data. Okay, and then the second part of her project was to combine these thresholds within the time series data, along with expert elicitation and a Bayesian event tree to come up with these eruption forecast models. So basically we had, I think, 3 or 4 iterations of this. Some of you in this room participated in these, thank you. So basically she provided the time series thresholds we did it for 4 volcanoes, we did it for Redoubt, Augustine, Pavlov, and Shishaldin. And the experts, who are either people at EVO or PREEVENTS collaborators, identified which threshold they thought was the most important for forecasting an eruption of this particular volcano. So this example here is for Pavlov. Some of the top 5 metrics identified were seismic tremor, acoustic tremor, SO2, and I can't remember the last one. Thermal, thank you, Terry. So yes, we did this for the 4 volcanoes, and she did a retrospective analysis, like a Bayesian event tree analysis for the readout to see basically using these, would we have forecasted the eruption? She's only done it on the first iteration when we were still learning, so I think she needs to update it with our, as we got better with our expert elicitations. The data are available. They're the same monitoring data we've shared before. And then the lessons learned, I think the expert elicitation was a bit of a learning curve for all of us. Most of us hadn't really thought in that way before, but we got better with practice. So I think the key here was, if you're committed to it, it can be really valuable, but it takes time and you have to practice. Okay, so this is not intended for you to read, but if you want to refer to later, this is a table summarizing the PREEVENTS data products that we developed through our project and what data are available. The top volcanoes are all one of the target PREEVENTS volcanoes, and the bottoms were other volcanoes that we applied, maybe because there was unrest or there was interest. So you can see what data are available. A lot of this data is published, but not all of it. But we've had quite an impressive, I think, amount of publications come out of this project, which is great when you have so many students and PIs and collaborators. We have 14 papers that are either already published or in press. 6 of them are student-led, which is great. And then the synthesis projects that I've talked about mostly, the ones Ronnie talked about are all published. The ones I talked about are all in prep, but we hope to have about 6 more papers coming out in the next year or 2. Okay, and then I'm going to completely switch gears, but the broader impacts portion of this project was to develop these classroom exercises focused on volcanic hazards and volcano monitoring, and we really wanted these to be useful to communities living near Alaska volcanoes, so the youth could learn about volcanic hazards and teach their community members. We were able to get a supplement when we submitted this proposal a long time ago. I think we didn't know some things, and we learned that the co-production of knowledge, incorporating local knowledge would be really important. So we actually wrote a supplement to the proposal and were able to get a little more funding. In addition to developing the classroom exercises, we also had a big outreach component to develop relationships with the native community of Perryville, which is on the flanks of Veniaminoff, and to ask them what they wanted, what they thought their youth should know about volcanoes. So we have two products that came out of this we're super proud of. The first is a YouTube video. It's called Piyuluk. It's the Sugstun name for volcano, which is what they speak in Perryville, or what their ancestors used to speak at Katmai. This is 16 minutes. It's kind of long, but I thought if there was a break at some time during the week, people might be interested to see this. This is some interviews with people from AVO or the PREEVENTS project, but it's mostly interviews from elders within Perryville, talking about their volcano observations and what they want people to know about their volcano. And then, yeah, the student guide is what's shown on the bottom. So we basically developed, I think, 6 or 8 classroom exercises targeting junior high or middle school level, focused on a different aspect of volcano monitoring or hazards. So those are really, we had design service help make this really pretty. So there's a background information, there's a classroom exercise itself, and then there's interviews with elders to tie it together. So that is not currently finalized, but we hope that we'll be able to share these on AVO's social media and other venues, so to get it out to the community. And then the last component is that we're going to be teaching these classroom exercises through a continuing education course offered to teachers through UAF this fall. So we're hoping we have money to bring in about 10 teachers from classrooms in rural Alaska that we're hoping to bring into Fairbanks and teach some of these exercises in person. Okay, some of the lessons learned from this project. It really takes time, effort, and persistence to build relationships in rural communities. I thought just calling and saying, hey, I'm from AVO, can you talk to me? I thought that would be enough. It was not enough. We were able to get an ambassador. We met someone in Anchorage who told her about the project. She got very excited. She used to live in Perryville. So she was actually the one that enabled us to really get our foot in the door for this. The second thing that was interesting is that the elders in Perryville, what they wanted their youth to know was not to fear the volcano. And that is not what I was expecting. I thought that was interesting, but I think probably if you go to any different community and any different volcano, they're gonna have something different. And so it's good to just keep this in mind. Okay, and then a synthesis of the overall lessons learned. So all the synthesis projects together. As mentioned earlier, the data are very variable. It depends upon your discipline, the time period, and the volcano. So depending on what project you're looking for, you wanna make sure that the data you need are gonna be available. Second, AVO color code is a good proxy for volcanic activity, but it should not be used for precise eruption start and end times. Often decisions are made through discussion within AVO to change color code. Often we think something's changed, but we want one more observation or one more satellite overpass before we make that call. So sometimes they're fairly accurate, but sometimes they can be delayed. Next, all data are nuanced. I think everyone knows this within your discipline, but it's really tempting to just use publicly accessible data without an expert to interpret. And I think within our group, we found that each student would start making interpretations on the data. And then when we would talk across disciplines, we'd be like, oh, you know, that's probably not what you think it is. So it's really important to try to incorporate an expert when you can. Multidisciplinary data synthesis is hard. You know, you have all these different observations. You're trying to find one unique solution. For us, we didn't find it to be particularly easy. Maybe there are volcanoes where it might be easier. But I think our lesson learned here was to really start the discussion early, involve all collaborators, and give people a way in. So you can present your ideas, get feedback, revise, iterate, and improve it to get something you're all happy with. And finally, this multidisciplinary collaboration was really beneficial and a great learning opportunity for all disciplines and all career stages. I think all of us who were lucky to be involved in this project felt like it was a valuable experience. And so I recommend any of you who have the opportunity to pursue something like this. Okay, my last slide, I just wanted to leave you. We did a lot for this project, but the project was ambitious. We didn't do everything that we proposed. There's still a lot to do. In particular, we are trying to present updated conceptual models for 8 volcanoes. I think we only did 3 or 4. In particular, the Cleveland and Veniaminoff are great candidates for more synthesis work. There's lots of data and they've had lots of eruptions. We also focused on forecasting eruption likelihood, and we just scratched the surface there. There's a lot more to be done on forecasting likelihood, but also forecasting eruption time, eruption size, and the associated hazards. And then finally, much but not all our data, models, and methods are publicly available. But our team would be happy to collaborate. As I mentioned, we'd love for you to build on the work we've already done. So if you are interested in using some of this, some of the data or some of the models, please reach out to the lead person as the project who was doing that. Thank you.
Does anyone have a quick question or two before we break for lunch?
Thank you, Taryn. Just this type of project, can you already extend it to other volcanoes, even without fire? Just using other data that are available, because you selected 8 volcanoes for PREEVENTS.
Yeah.
So can you apply for other volcanoes who were not selected in the first place?
Yeah, and we did. We found that when there was unrest at a certain Alaska volcano, like Darren would be one of the first person, he would run his model. Okay, what's the seismic tremor character or something like that. So we did apply it when possible. I think having the tools in place and the data available is, it's a barrier. So that when you're past that, you can apply it more readily. But it will depend on each discipline. Jeff.
Yeah, I love the multi-plot tool. That looks great. How transportable and generalizable do you think that is? Is it really closely integrated with ABO databases, or would it be potentially straightforward to apply a similar tool to, or for somebody to build more general databases?
We talked about it. So our project runs out of funding next year. So ideally we would make it publicly available. As it's currently written, there's non-public data. So basically data that's, preliminary internal use only. And so it probably wouldn't be hard to screen out and make a separate login. I'm not sure. We've thought about it, but we haven't gone beyond that. But yeah, I agree. It would be nice to make at least the publicly available data and the tool available. We don't have our programmer here, so I don't know. Ronnie, do you have anything?
I think the tool right now is probably, it is very well integrated with ABO databases because it has to. That's where it pulls the data. But the interface itself is probably with some effort generalizable enough to pull that away. I just don't know how much sense it really makes to have that if you don't also have the databases with all of that information for a lot of different kinds of volcanoes.
Yeah, I was thinking in the context of, for example, SC4D, with all these multi-parameter observations, generating, building a more generalized tool, actually something that we should.
We're happy to collaborate.
I've done some synthesis work for seismic results alone at some locations in Alaska and all the places. So I'm wondering, since you're basically synthesizing multidisciplinary results from your projects, I'm wondering what for seismic results alone, there could be multiple groups, multiple methods that are getting similar or different results. So how others could contribute to some of the volcanoes you have studied with all similar discipline but different results or different methods. So how the contribution process works.
I think there's certainly room for expansion. We were kind of time limited. This work was led by students. I think almost all of them have graduated now. But yeah, we had to prioritize which method we were going to apply, but there's certainly room for expansion. So we're out of funding at this point, but I think we would welcome other people to build upon the work and apply their technique and collaborate as needed.
Maybe just an addition, right? So there was a lot of literature review and then kind of trying to harmonize our own findings with the application of the tools to the old data to see once we review what has been done in light of the new results, like how these things kind of come together. There were obviously, you'll see in the papers that there are things that don't agree with what we found, and then it's being discussed why that may be.
It's fantastic that all the tools look like they're available through GitHub and open source. Are there plans to integrate them with cyber infrastructure platforms like Victor or similar things?
We haven't talked about it. I think, yeah, we're open to collaborations.
Last week.
Oh, okay, Ronnie's talked to him now.
Awesome, yeah, that's a picture.
Oh, yeah.
Hi, Taryn. I was wondering if you, was there an attempt maybe to sort of arrange the information in a hierarchy of sorts or some grand template that might be a systematic way to figure out where the biggest gaps are that are preventing certain things from being learned?
I'm not entirely sure I understand, but what we did do when we were writing the proposal is we made a big table of the volcanoes we thought were the most interesting, the eruptions they had. We were looking for a combination, right? We needed observations and eruptions. And so we tried to just say, okay, well, these volcanoes have a lot of eruptions and they have some disciplinary observations, and then these ones have different ones. And so we kind of tried to find a balance of different volcanoes with eruption styles that also were hazardous, like erupting frequently or close to, Anchorage. That's is that what you were asking? And how do we prioritize it?
That's close enough.
Okay.
All right, well, thank you
Thank
so
you.
much.